Okay, hello and welcome back to the second part of digital computer electronics. This time we're actually going to get into some breadboard prototyping. We're going to look at logic gates and building those in transistors and diodes. As you can see here, I've set up a binary number, or a few LEDs technically, to show a quick recap of last time. So this is a binary 1101 0010 as on, off, off, on, off. That was really difficult to say, surprisingly. So we have this binary number here. Now, as you remember, this is the 1s, the 2s, the 4s, the 8s, etc., etc. So if we want to decode it, we have to look at all of those numbers and strike off the ones that aren't there. So like so. And then we just add all the ones that are remaining up, and we end up knowing that 11010010 is equal to 210 in decimal. So there we go, a quick recap on binary numbers. So if you want to, you can also convert that into hexadecimal, which I think would be D, is that D? Yep, D2. So yeah, quick recap there of binary numbers. Right, let's get into it. So we're going to be looking at using the breadboard. So this is a breadboard. I have here a little power supply. These are called LEDs, light emitting diodes. There's a lot of explanation as to what a diode is on the internet, so I won't bore you with the details. Suffice it to say that a diode will allow electricity to flow one direction only. And a light emitting diode will allow it to flow in one direction, but also make a lovely little light. There we go. These things here are resistors, so they resist the flow of the voltage and the current, etc. I do have a video on Ohm's law, which explains this a little bit more. So if you want to have a little look around on the channel, that will be there. And we're also going to be looking at transistors. Now I have a few transistors here. So here we go. This is a transistor. Let's bring it closer to the camera here. Come on, focus, you little beggar. I think that's focused as it's going to get. So this little thing, it acts kind of like a switch for electricity. Now, I do actually have a push-button switch here, so we're going to be using these as our inputs later, so a little push-button switch and a transistor. So the push-button switch actually requires a human to touch it, to press it, for it to actually do. The transistor requires electrical current to activate it. So here we go, we've got a circuit diagram representation of the transistor here. So we have a base, a collector, and an emitter. This is what's called an NPN transistor. There's another type as well called a PNP, which is slightly different, but this is the one that we're going to be using. You can find details on the web for the differences between the two. So just for the sake of brevity, this is what we're going to do. So the base is basically where our signal will come in. The collector collects the current, and as long as the base is switched on, it will emit. So pretty much like a push-button switch kind of thing, but that's the circuit diagram. Okay, so this is the internal workings of a transistor. There's much better explanations on the internet than what I'm about to do. This is a really cut-down version. But basically, it's three little pieces of silicon. Silicon, as we know, does not conduct electricity. So it's been doped with phosphorus and boron. It's kind of like two diodes put together. So a diode would be like this, so electricity can only flow in one direction. It kind of makes a barrier here if it tries to flow in the wrong direction. So with this piece of silicon in the middle that's been doped with boron, electricity will not be able to flow from the collector to the emitter without the base saturating this with electrons. So then it'll be able to flow nice and freely through. So it'll come through the emitter and pull current through the collector. Very, very basic explanation there. And the ones we're going to be using are the 2N3904s, which look a little bit like this. You saw one a little bit earlier, looks like that. It's got a flat face, focus. It's got a flat face at the front and a curved bit at the back. And going from left to right, looking at the flat face, it's emitter, base, and collector. Okay, so that's a very, very basic introduction to a transistor. Right, let's get onto those logic gates, shall we? So, the first one we're going to look at here is called the inverter. And this is a very, very simple logic gate. So basically, voltage comes in, and it does something here, and then some voltage comes out. What the inverter actually does is, if we have a positive voltage coming in, it will actually output nothing. If there's nothing coming in, it will output something. So here we have what we call a truth table. We're going to be looking at these quite a lot throughout this video. So voltage in is off, voltage out is on. Voltage in is on, voltage out is off. So 0 and 1, as you know, is the binary representation of on and off. So 0 is off, 1 is on. So when we look at our little lights here, you can see these ones are on, this one's off. So this is 1, 1, 0, 1. So that's basically an inverter. It's a very, very simple circuit. And we have here a circuit diagram for an inverter. Now you see this inverter uses a transistor. What happens here is we have the voltage coming in here and into the transistor's collector. We have our voltage in hooked up to the base, and it comes down here to ground. Now what will happen is this will go through voltage out. Let's assume this has got, say, an LED connected to ground. So when this comes on, there's nothing coming through here, and it will just sink through here into the ground and light up our little LED. Okay. When we apply a voltage here, it's going to saturate the base. The current's going to come all the way down through here. It's going to pull it down into ground, and this LED will go off. Show you what I mean. I'm going to build this circuit on a breadboard, and we'll have a look and see how it actually works. Okay, so here is our inverter built on a breadboard. As you can see, we've got our transistor here. What we've done is we've connected the emitter of the transistor to the negative power rail, just like in this diagram here. We've connected the collector, which is this leg on the far right here, to the positive rail via a current limiting resistor, and we have our output jutting out to the side here. So you can see it's the same as that. And finally the base, which is in the middle, we've connected via current limiting resistor to this little tactile switch, which is connected to 5 volts. So when this will go high, this light should go off, and when this is low, that light will be on. Right, so we've got no input here, and I'm going to turn the circuit on. So what we're expecting, based on our truth table, is when there's no input, there will be an output. And then when I apply an input, the output will go off. So let's just see if that works. So power on, there we go. So no input, and we have our output. If I press this button, our light should go off. And it does. There we go. So that is our inverter. So there we go. It works fine. So why does that happen then? Well, looking at this, I'm not going to make this explanation for everything else, but basically, when this is in its normal state where there's no input here, this will actually be a closed circuit. So it's going to be lighting up the LED that's on the V out. What's going to happen when I press the button, it's going to saturate this transistor and pull all the current down into ground. It's going to create the connection all the way into ground and draw it down. So it's going to bypass this, come straight into ground, and nothing's going to come out of here, or maybe some very small amount of current. What I will do is I'll quickly build this up on the computer as well, on a simulator. And if I run the simulator, you can see here that the current does indeed sink down to ground when I activate the input. So yeah, you can see quite clearly what's going on with this electronic simulation of a circuit. Okay then, moving on. This is the algebra, so Boolean Algebra is great fun. We're going to be coming into that later, but I just want to introduce you to it. So NOT. The inverter is generally called a NOT gate. And normally what we'd do is we'd put a line above something to indicate that it is inverted. So here I've got Y inverted, it should be V in inverted. So yeah, just remember that. When there's a line above something, it means it's an inverted output. Okay, let's move on to the next gate, which is called the OR gate. So here, this is the symbol for the OR gate. So we have 2 inputs. You can have more than 2 inputs. You can have 5, 6, 7, 8, 9, 10. You can have as many inputs as you want onto an OR gate, and a single output. Okay, the truth table for this looks like this. So it's a little bit more complicated because we have 2 inputs now instead of just the 1. So here A, B, Y. So an OR gate. So if A or B are on, then Y should be on. The only time the output is 0 is when there's no input on either of them. What does an OR gate look like? It's a lot simpler. So an OR gate looks like this. We don't need a transistor to build it. We can build them with transistors, but the simplest way to do it is with diodes. Now, a diode would only allow current to flow in one direction. So if we have an input here and that goes high, it won't flow the current back into input B. So it'll just flow through here and go to our output. Okay, why is this going to ground? The reason why that's going to ground with the resistor is what's called a pull down. It makes sure that there's no floating voltage, so it accidentally goes high. You'll find this happens quite a lot in microchips. Okay, you can, as I said, build it with transistors, and that's what a transistor version of an OR gate would look like. It is quite complicated in comparison. So it's a lot easier to build OR gates with diodes than it is with transistors. So let's break out the breadboard and build an OR gate. Okay then, here we go. This is our OR gate. So we've got our two inputs here, two little buttons. We've got the diodes going into our output, current limiting resistor for the LED, and we've got a resistor pulling it down to ground to make sure there's no floating voltage. So when we power this on, we can see nothing is working. If we turn this on, the LED comes on. If we turn this one on, the LED comes on. If we have them both on, the LED is on no matter what. Okay, so there we go. That's our OR gate. So one or the other comes on, then the light will be on. So that is exactly what we were expecting from our truth table. So very simple to build an OR gate there. Yeah, so an OR gate would actually look like this. This is the output. Now, I know what you're thinking. That looks like an AND, A and B, but it's not. In Boolean Algebra, the plus actually stands for OR. So this is A or B, and that will be the output of the gate. Okay, and the last one I want to do today is the AND gate. So the AND gate looks like this. This is the logic symbol for it. So two inputs again and one output. But again, you can have more than two inputs. You can have 3, 4, 5, 6. You can have as many inputs as you want to. Let's look at the truth table for this. So you see here, different to the OR gate. So this is an AND gate. So A and B must be on in order for Y to be on. Okay, so the transistor version would look a little bit like this. So we have our load here, which is our Y. So this is going to be our diode. And so when A and B are both on, this will come down into ground. Now, the reason why it's not coming off to the side is because if it was coming off to the side, that would indicate that that's going down to ground, and that would be a inverted AND gate, which we'll come on to in the next video. So for the purposes of this, we're just going to put it right here. Righty-ho, and here we go. This is our AND gate. As you can see here, it looks a little bit complicated. Basically what we've got is we've got two switches. So this is our input A and input B. So we've connected the switch to the positive rail here and the positive rail there. This then connects via a current limiting resistor to the base of each of our transistors there. The emitter is connected to ground. The collector of this transistor is connected to the emitter of the next transistor. There's nothing in between. And then the collector here is connected to our LED via a current limiting resistor to the positive rail. So it's very similar to our diagram, which is here. It looks a lot easier on the diagram than it does on the board. So if I power this circuit on, we press one button, nothing happens. We press the other button, nothing happens. If we press both of the buttons, the LED will come on and bathe us in a nice warm red glow. So one or the other, nothing. Both of them together is AND, and that's the AND gate. For the Boolean Algebra fans out there, this is what AND looks like, A dot B. You can also remove the dot and just have AB together, and that signifies AND. Right, that's all we have time for this video. If you liked it, please hit the like button. We have some more logic gates coming up. They're slightly more complex. But that's all for these basic ones and a quick introduction to Boolean Algebra. So until the next time, for the next video, thank you very much for watching. Please like, comment, subscribe and share, and I'll catch you later. Bye bye. Wobbly fingers.